Here we take a look at the alkene hydrogenation reaction. In many ways, this is a reaction that seems very, very simple. We take an alkene, we add hydrogen gas in the presence of a palladium on carbon catalyst. This can also be a number of other metals, such as nickel or platinum, among others. But the alkene gets a hydrogen added to each carbon and gets converted to an alkane. So very, very straightforward reaction on that level. This reaction has been known for quite some time. It's originally credited to Sabatier in the late 1800s, and he also shared the 1912 Nobel Prize in Chemistry for this reaction. How does this work mechanistically? So one of the things I want to say before we get into its mechanism, whenever we have reactions that involve transition metals, such as this one with palladium, the mechanisms tend to work a lot differently than they do for other types of reactions. And so what the palladium does is we're going to just consider this our surface of the palladium metal. And so both the alkene as well as the molecules of hydrogen gas will essentially coordinate to the palladium metal. And this allows them to be in close proximity to each other, which helps them to react. So from here, one of those hydrogens transfers over onto the alkene. And then the other hydrogen remains on the palladium. And then basically this process repeats. The other hydrogen comes over as well. And we end up with the addition of these two hydrogens, which converts our alkene into an alkane. So because of the way that this reaction takes place, it's important to keep in mind that the addition is cis, or in other words, the two H's add from the same side. And for a molecule like this, that doesn't really make a difference. But if our starting alkene is more complicated, then that has consequences for the product. So an alkene like cyclohexene will get converted to cyclohexane. But if we have substituents on there, such as a pair of methyl groups, then what will happen is that because the two hydrogens have to add from the same side, and that could both of them be down or both of them be up, it also means that the two methyl groups will end up on the same side as well. So the hydrogenation using palladium on carbon is lets us convert alkenes to alkanes, and does it by adding two hydrogens to the alkene from the same side of the molecule. And we can demonstrate here, we've probably said this many times by now. Aromatic rings are not alkenes. And so if you try a hydrogenation with an aromatic ring present, the aromatic ring will not be affected by the hydrogenation. So the aromatic ring stays intact, but the alkene gets converted to the alkane. Are there functional groups that you need to be concerned with hydrogenation? The main one is alkynes can also be affected by hydrogenation. And then some very specific carbonyls. Not all carbonyls. In fact, not most carbonyls. But especially if you have a carbonyl that's right next to an aromatic ring, that can get affected by a hydrogenation reaction as well. So where might we run into a hydrogenation reaction? Well, probably the most important example are for molecules like this. Long chain carboxylic acids like this are fatty acids. They're what make up fats. An unsaturated fatty acid is one that has an alkene in it. How does that get converted into a saturated fat? Well, through a hydrogenation reaction. But hydrogenation is also a very important reaction synthetically. And a good example of that is going to be here. So if we start with this alkene, one of the more recent things that has been done in hydrogenation research is if you look very carefully at this carbon. The carbon that I've highlighted in green has a carboxylic acid attached to it, a nitrogen group, and a carbon group attached to it. So if we add a hydrogen to that carbon, that's going to make a chiral center. And one of the things that chemists wanted to figure out is if we're doing a hydrogenation that makes a chiral center, is there a way that we can make it only R or only S? And so instead of just using a simple palladium catalyst, there's a lot of phosphorus and aromatic based catalysts that are chiral. And so if you do this hydrogenation with H2 and a chiral catalyst, then when you actually do the reaction, not only do you get as expected, you get the addition of the two hydrogens, but notice we only get one enantiomer at the new chiral center. And work like that was so important that this idea of asymmetric hydrogenation, that back in 2001, Naori and Knowles shared the Nobel Prize in Chemistry for this work. Now, the specific example I've shown you here, if this undergoes just a couple of additional reactions, remove this methyl group, as well as remove this carbonyl, then you form this product, and this product here, and this path, is how you can make L-DOPA, which is a fairly important drug in the treatment of Parkinson's disease. So, although the alkene hydrogenation to an alkane, certainly seems like one of the simplest reactions we have. Again, it's just adding two hydrogens to an alkene to make an alkane. It's one of those reactions that's been extremely well studied and has a lot of useful and very, very important applications.